Good morning. My name is Evan, this is Alec, and we are Team Cambridge Technology. Our project is stepper motor motion control for scan system. Now, I will begin with a brief recap of our project motivation and goals. Cambridge Technology develops galvo-based laser scan heads, which can be used for a variety of production purposes. This includes drilling, etching, and many more. One inherent limitation to their product is that it operates in a fixed position. This means that it can only scan over a set XY plane. The purpose of our project is to add the capability to their product to control one or more stepper motors, which can be used to drive linear slides. The purpose of being that the user can attach the scan head to the linear slide and move it, thus changing the XY plane over which they can scan. A visual representation of this purpose can be shown here, where the user would attach the scan head to the slide, and in the forwardmost position, they have a smaller scanning area. And then through the same software that they use to program the scan, they can ask the slide to move backwards and thus change and increase the scanning area over which they can work. Now, this project is split into three major portions. The software, which the user gives a move command to, will then generate what we call a motion profile. And then this motion profile is delivered to the hardware, which translates the profile into voltage pulses, which then control and drive the slide and motor. The final portion of the project was to integrate our hardware and software logic into Cambridge Technology's ScanMaster control board and ScanMaster design software. Now, we are happy to say that all three of these goals were achieved, and our final anticipated outcome was fulfilled. In this next slide, you will see where we were at the halfway point in the year. Here, we only have the lowest level of control, which is through the hardware, which means once we set the behavior for the slide, you can no longer change it once the board is running. You will also notice that the slide has jagged direction changing and starting and stopping. In the next slide, you will see what we accomplished over the coming months was we added We added the software, which allows us to send multiple commands, one after the other, from which we can change the distance that it moves over, the direction it's going, as well as the velocity that it's moving at. You'll also notice that it has acceleration and deceleration at start and stop. This reduces and puts the least amount of possible force on the scan system. Next, my partner Alec will go into how we achieve this.
So a little bit about the key accomplishments here. Although there are three main portions to our project, the hardware, the software, and then the final system integration, there's really one underlying component that drove the whole thing, and that is what we've called the motion profiling algorithms. And what it really is a translation layer. You know, once the user calls our system to move the motor or the slide at least, 300 millimeters, the motor doesn't actually know what that means. You can't just send 300 to the motor and expect it to do something. Likewise, since it's a stepper motor, you can't send 300 randomly spaced pulses and hope that it works well. The level of precision in this application is far beyond that rudimentary approach. So there has to be some translation between the user saying move 300 millimeters and the actual electrical pulses delivered to the motor. And that's what this is here. The algorithm is really the translation. And what you're seeing on screen here is just a curve of the velocity of the pulses or the spacing of the pulses being sent to the motor as a function of the total number of pulses that need to be sent to move the motor X millimeters. Now, this is something we had to develop before we had the hardware or the software in place to actually test in the real world. We had to develop a simulator to do so, to make sure that we had the algorithm pat down, that we had it robust enough to handle every use case. And there were a lot of use cases that we simulated. As you can see here, this is just a fraction of all of the different scenarios we were able to pass over our algorithm, see the output, see if it met the requirements, see if we needed to make any changes or if it was good enough under all scenarios. This was really helpful because we didn't even need to power on the board to know exactly what our algorithm was going to do. So the first major component was the software. So we implemented the algorithm I just described in the previous slide in C++ and provided some software structures for easy interfacing. But more importantly, we provided an easier API to the upper layers and specifically the user. This is it. This is the only command that the user has to specify to interact and move the platform. It's just one line. You just reference our motion profiling schema or platform, Tell us which axis you want to move on in the event there are multiple motors in the system. Tell us how far you'd like to go. Tell us in which direction you'd like to go that distance, and then how fast you'd like to get there. And then we take care of absolutely everything else from that point on. Hardware is a little different. It's quite a bit more complicated, but it's not something the user actually has to directly interface with other than plugging their motor into Cambridge Technology's I/O board on the ScanMaster controller. But the point here is, with the exception of the AXI interface at the top, which is a protocol that was already in Cambridge Technology's system, everything you see was completely designed from the ground up by us in Verilog, which is a hardware description language. We didn't import any libraries. We didn't use any third-party services. This is all completely synthetic. The degree of difficulty here was pretty high because Verilog is a language that neither one of us had ever seen before or developed in, and the level of digital design here is quite a bit beyond the introductory digital design that you might get in an undergraduate curriculum. So finally, the system integration here. We took the hardware and the software that we had designed and placed it into the full production commercial system that Cambridge Technology sells. And as I'm sure you know, the integration of one project into another almost never goes smoothly. There were a lot of speed bumps in the way, but our technical directors, in working with us, we were able to achieve this goal and maintain all of the simplicity of the APIs that we had originally designed. As you see here, we even added a motion config command, which basically just changes the environment parameters. In the event that you have a different motor or a different slide, they're going to have different parameters, and that's going to change the math behind the scenes. So we allow the user to set that in one line, and then you just call our other one-line API to actually move the motor, press the big green button, and it's good to go. So here you'll see a demonstration of just exactly how the user would interface with our motion control project. They can specify as many move commands as they would like, then press the big green button. And there's a lot that goes on between the press of this button and the motor actually moving the slide, but we take care of all of that under the hood, and the user never has to really know about that. One thing I want to make clear here is that this is just a motor plugged into a piece of metal. Every bit of intelligent movement and seemingly intelligent motion profiling is done completely by us ahead of time, mathematically and algorithmically. It's all done completely theoretically. And you can see just how precise it gets here, right up to the end. So with that, I'd like to thank everyone who was involved in this project.